We'll now continue section 1.6 and discuss absolute value linear inequalities. There are two absolute value linear inequality rules that we must be aware of as we begin to work problems. The first rule deals specifically with a problem that has a less than in it. This rule says that if we have the absolute value of x is less than a number a, then this means that in order to solve the inequality, we must write it as a combined inequality with the three parts. Our other rule says that if we have the absolute value of x and it is greater than a, then we will work the problem by writing two problems, one of which looks just like the original without the absolute value, and the other one will look like, we'll switch the inequality to a less than, and we'll put a negative on the a. And so you have to pretty much know this in order to work the problems. You have to know that less than absolute value problems work one way and greater than absolute value problems work in a different manner. So let's begin with our first example. Our first example is the absolute value of 4 minus 2x is greater than 6. So since it is a greater than problem, it is going to be approached in that manner with two separate problems. And so one problem, remember, is going to look just like the original. 4 minus 2x is greater than 6. The only thing that we do is we drop the absolute value. The other problem is going to be 4 minus 2x. We're going to switch the inequality to a less than, and we're going to put a negative on our answer. And now we'll work both of these inequalities out, solving for x. So we begin by subtracting 4. And I'm going to just go ahead and work both of them as we go. So this, on the first one, we're going to have negative 2x is greater than 2. On the second one, we're going to have negative 2x is less than negative 10. In both cases, we're going to divide by negative 2. Now remember that when you divide by a negative and you're working on an inequality, you are going to switch the sign of that inequality. So we have x is less than negative 1, and we have x is greater than 5. And so if they ask you to graph the solution set, you can see that we have it graphed here. We have the negative 1, and we have an open parenthesis on the negative 1 because there's not an equal to on our inequality. And we're shading everything less than that, so everything back to the left. Same thing on the 5. We have a parenthesis because it's not equal to 5, and we've shaded everything to the right. If we're asked to write our answer in interval notation, we'll start on the most left-hand point, which is negative infinity. And we say that our answer set goes all the way up to negative 1. Negative 1 has a parenthesis. It picks back up at 5 with a parenthesis and continues all the way to infinity. Remember that your infinities always get parentheses. All right, let's look at a second example. This is actually part B of this example. We have 2 times the absolute value of 3y minus 2 plus 3 is less than or equal to 11. And so in order to work this problem, we need to first isolate that absolute value so that it looks more like this problem that we started with here, where we had an absolute value and we had everything else on the other side. So let's see if we can do that. I'm going to subtract the 3 off. So it's going to give me 2 times the absolute value of 3x, or 3y minus 2, is less than or equal to 8. And then I'm going to divide by 2, which gives me the absolute value of 3y minus 2 is less than or equal to 4. Now, recall that if we're working a less than problem, that we want to set it up this way, with a combined inequality with 3 parts. So we're going to take this 3y minus 2, and we're going to sort of sandwich it in between the positive and the negative 4. And then we'll work at solving that inequality. So we'll begin by adding 2 to all 3 parts, which is going to give me negative 2 is less than 3y is less than or equal to 6. And then we're going to divide all 3 parts by 3. So that's going to give me negative 2/3 less than or equal to y less than or equal to 2. If we want a graph, you can see that the graph is done here. We have a bracket on the negative 2/3 and a bracket on the 2 because of the equal signs, and we've shaded in between. If we want to do interval notation, we start with the bracket on the negative 2/3. We end with the bracket on the 2. Okay, part C. We have the absolute value of 5 plus 2s is less than or equal to negative 3. Now, we want to be careful here because we know that an absolute value does what to a problem? That when I take the absolute value of this 5 plus 2s, what does that absolute value do? It always makes it positive. And so our problem is basically saying what positive numbers are less than or equal to negative 3. And that's never going to happen. We're never going to take the absolute value of something, causing it to be positive, and then have it be less than or equal to negative 3. And so since that's the case, the solution set is the empty set because it's impossible for that absolute value to be negative. And so we can say that the solution is and we usually write it that way, that's the empty set, or you can just simply say that there is no solution to this absolute value inequality. Okay, our last part, 5 plus 2s in the absolute value is greater than or equal to negative 3. Now again, we want to be careful here. We want to think about this. For what s values is this going to be true? I'm going to argue that it's true for all of them because when I plug an s value into this problem and then I take the absolute value of it, remember that it doesn't really even matter what is here. When I take the absolute value, it's going to produce a positive number. And what positive numbers are greater than or equal to negative 3? All of them. And so we're going to say that the solution is, and we're going to write it as all real numbers. Okay, or you could say negative to positive infinity, but every s value will make this a true statement. Okay, so the last thing that we're going to talk about is we're going to talk about some particular wording that we'll see in some of these problems and how we translate that into mathematical expressions. So we're just going to look at these for just a second. One thing that we'll see quite a bit of is this phrasing here, x is no greater than y. And so we need to be sure that we understand what that means. If x is not any greater than y, then it has to be either less than or it has to be equal to. All right, so think about that, make sure that makes sense. We're saying that x is not greater than y, so therefore x has to be less than y, or it could be equal to it. All right, here's another one. X is at least as large as y. When you say that something is at least, you're saying that that's the lowest that it possibly could be, but it could be bigger. So we're saying that x is possibly equal to y, or it is larger than y, in order for it to be at least as large as y. The third phrasing is for us to have it say x does not exceed y, which means that x does not get any bigger than y. So that means essentially that x is less than y or possibly equal to it, but it cannot get any bigger than the y. Okay, so let's look at a couple of examples. Express each of the following problems as an inequality and then solve that inequality. The part A says the average daily temperature in Santa Fe, New Mexico over the course of 3 days exceeded 75. Okay, so right now I know, and I'm just going to kind of jot this down as we go, we know that the average exceeded, which means that it was greater than 75. Given that the high on the first day was 72 and the high on the third day was 77, what was the minimum high temperature on the second day? Okay, so how are we going to find this average temperature? We're going to take the temperature for the first day, which was 72. We're going to take the temperature for the second day, which is what we're looking for. We're going to call that x. And we're going to take the temperature for the third day, which was 77. And to find an average, we'll add those three together and then divide by 3. So we're essentially saying that that average has to be greater than 75. And so in doing that, we set up an inequality that we can solve. Okay, so let's look at solving this. 72 plus 77 plus x divided by 3 is greater than 75. Again, to solve this inequality, we probably want to get rid of our fraction. To get rid of our fraction, we can multiply both sides by 3. That would cause it to cancel on the left, leaving me 72 plus x plus 77. On the right, 75 plus 3 would be 225. Now, as we go to solve this, 72 and 77 make 149 plus x is greater than 225. And so then if we subtract the 149 from both sides, that's going to give me x is greater than 76. And so the high temperature on the second day has to exceed 76 degrees. All right, so let's look at part B of this same kind of problem. So a little different situation. It says, as a test for quality at a plant manufacturing silicon wafers for computer chips, a random sample of 10 batches of 1,000 wafers each must not detect more than 5 defective wafers per batch on average. So they test 9 batches, and the average number of defective wafers per batch is found to be 4.78. What is the maximum number of defective wafers that can be found in the 10th batch for the plant to pass the quality test? So let's think about how we're going to average these 10 batches together. We know that for the first 9, the average is 4.78. And so if I want to look at those 9 together, I would say 9 batches. Each one has an average of 4.78, so we can multiply those two together. That'll take care of the 9 first batches. Then we just have to look at that 10th batch. And that 10th batch, how many defective wafers can be found in that one? We don't know, so we're going to use an x. And remember that we're calculating an average, so we're going to add all this up and divide by the 10 sample batches. And we want that to have no more than 5 defective wafers. So this number of defects has to be less than or equal to 5. All right, so let's take a look at solving that expression. What would we need to do first in order to solve that inequality? We would more than likely want to multiply both sides of the inequality by 10. Which would cause it to cancel on the left. And 5 times 10 would give you 50 on the right. 9 times 4.78 gives you this 4302 that we're looking at right here. All right, next step would be to subtract that 4302 from both sides. And that should finish up our problem for us, saying that the x has to be less than or equal to 6.98. Now, you do want to keep in mind that it's not possible to have a fractional number of wafers. So therefore, there must have been 43 defective wafers in the first 9 batches. All right, so not 43.02 as we came up with right here. So the maximum allowable number of defective wafers in the final batch would have to be 7, would not be 6.98 as we came up with before. So we just kind of want to keep that in mind, that those numbers do have to be whole numbers.